remember. Now, right at the end of the last lecture, I said that some simple alcohols have some trivial names. And I put up this alcohol, which is called methanol, and I put up this one, which is the stuff people drink, and I also put up this one, and I said it was either isopropyl alcohol or it was 2-propanol. And right at the end, at a time when some of you rather impolitely just got up and walked out and it wasn't at the end of the lecture, that happened a number of times to one of my colleagues, a very famous professor in Massachusetts Institute of Technology. And there, the professors can be as impolite as they want. You can't do that here. You have to be very, very polite here. That's why I'm very, very polite. But what he did is he stopped talking. There was a moment's silence, and then he said to the class, "I hope your grades are better than your manners." That's what he said to the class. He didn't have any more trouble with them after that. Anyway, right at the end, when a number of people walked out, perhaps they were hallucinating and thought they heard a fire alarm or something like that, if one wants a charitable explanation. I put up this compound, and I said you could either call it tert butyl alcohol, or you could call it 2-methyl 2-propanol. Now those are the few names that I put up. What I'm going to do now is to put up a few more names, and then I will put up a few names of a class of substances called ethers. You remember when I started to talk about alcohols, I wrote down 3 structures. I wrote down water, and I said if you didn't know that that was a formula of water, you should drop the course. And then I wrote down a picture like that, and I said those are alcohols, and finally I wrote down a picture like that and said those are ethers. So there's a series of compounds, water, alcohols, ethers, and so we're going to deal with them more or less at the same time. But before I do that, I want to put up a few more names of simple alcohols, and after that I will explain to you how to name a very complicated alcohol. And this name here is an example of how to name a reasonably complicated alcohol. But I will explain what's going on, why there's a 2-methyl, why it's a propan, and why it ends in ol. But first of all, I just need to put up a few more examples, which I will now do. This is allyl alcohol, or 2-propanol, and in a few minutes when I tell you the rules for naming reasonably complicated or very complicated alcohols, you will see why this name comes into existence. This one here is called propargyl alcohol. Or 2-propinol. That is benzyl alcohol. Now, a moment ago I said that not all substances that have an OH group attached to carbon are alcohols. And I've just drawn up one of them. This one is called phenol. Now, in a sense, it is a type of alcohol, but its properties, it has so many different properties from ordinary alcohols, in which an OH group is attached to an alkyl unit, that we deal with these as a compound class in their own right. So it is an alcohol in a sense, but its properties are rather different from those of allyl alcohol or methanol or ethanol and so on. So that's enough about very sort of common names of alcohols. I have written up a few systematic names, but I haven't explained how to work them out. What I'm going to do now is to write up a few common names of ethers, and then I'll go and explain to you how to systematically name an alcohol. Now, the most common ether, the one that everybody has heard about, is this, which is called diethyl ether. It's a volatile liquid. It burns with quite a cold flame. You can set it light, put your hand in for a moment, it won't hurt you. Don't try that, but you could do that. This one is called allyl methyl ether. Okay, there are some names of ethers, and one of the things that I'm sure you will have noticed is that you use the word ether to indicate that you're dealing with that compound class, and then in alphabetical order you identify the alkyl groups or the aromatic rings that are on either side of the oxygen. So here we've got a tertiary butyl group on one side of the oxygen and a methyl, so it's tert-butyl methyl ether. Here we have a phenol group and a methyl, so it's a methyl phenol ether. Here it's a diethyl ether. Here there's an allyl and a methyl. So one of the ways of naming ethers is just to use the word ether, so people know that there are 2 carbons on the oxygen, and then you identify what the carbons are. If it's a methyl and ethyl, then it would be ethyl-methyl ether, or methyl-ethyl ether. If it's 2 propyl groups, it's dipropyl ether. You usually put them alphabetically. So what you've had in the last few minutes is a miscellaneous list of examples of some alcohols and some ethers. Now I want to tell you how to name these things systematically. So I'll first deal with alcohols, and then I'll deal with ethers. Now you will have noticed that many compounds have more than one name. Sometimes they have what's called a trivial name, and they all have a systematic name. And unfortunately, you have to know the trivial name, and you also need to know how to write down the systematic name. Now, for alcohols, what you do is you identify the longest chain in the compound carrying the OH group. So, supposing we have this substance. This is the compound we've got to name. Now, the longest chain carrying the OH group is this one. I could also put the 5 there because the chain is the same length since these 2 groups are identical. That doesn't matter. But you see, if I start here and go this way, it's only 3 carbons. If I go this way, or if I go that way, it's 5 carbons. So I identify the longest chain carrying the OH group. And that chain is this one. And then I number the chain from one end to the other. Now there are only 2 ends to a chain, and so I can write down 2 pictures, and I can number one picture from the left and the other picture from the right. And I have to give the lowest possible number to the carbon carrying the OH group. So if I number it this way, the carbon carrying the OH group has the number 1. But if I start numbering here, the carbon carrying the OH group has the number 5. And 1 is lower than 5, obviously. And so this is the correct way of numbering it. Now, that longest chain is a 5-carbon chain. Now, when somebody says to you, name a what do you think of when somebody tells you to think of a compound having 5 carbons, you should say pentane. If you don't, there's something wrong with you. You know, I understand that psychologists play little games. They say dog, you're supposed to say cat. If they say dog and you say hippopotamus, the guy's a bit crazy. I mean, sometimes it's useful to know what answer they expect, because you can use that to your advantage. There was a very famous case, a Nobel Prize winner in physics, who was called up to be evaluated to see if he could serve in the United States Army. So it's like you have to go through all sorts of medical tests and so on. He seemed okay, then they passed him on to the psychologist. And this guy was a Nobel Prize winning physicist. He didn't want to spend his time in the army, he wanted to do his research. The psychologist said, hold out your hands. So he did this. The psychologist said, no, the other way. So he did that. They decided he wasn't fit for military service. So he went back to his university and continued his research. So sometimes it is an advantage to know what answers they want. But if they ever ask you 5-carbon compound and you say something other than pentane, they will be worried. So you think of the word pentane, and the rule is that then you cross off the final E and add the letters OL, because that tells you you have a 5-carbon piece with an alcohol, an OH on it. So that gives you the name pentanol. Now, on this 5-carbon chain, you have to indicate certain things. You have to indicate where the OH or the OL is, and you have to indicate what the substituents are and where they are. So the substituents are methyl groups, so there are 2 of them, so it's dimethyl. So this is a dimethyl pentanol. But now you have to indicate where these groups are. And so it is in fact 2, 4, dimethyl, 1, pentanol, or 2, 4, dimethyl, pentan, 1-ol. There are a couple of systems in which the number for the last named group is put as late as possible, and another system in which it's put as early as possible without causing confusion. So if you put it here, 1-pentanol, there's no confusion. It's a pentanol, and at position 1 is the ol. You could also put it there as pentan 1-ol. So that is an example of how to name these compounds systematically. Identify first that the substance is an alcohol. That means the name's going to end in OL. Second, identify the longest chain carrying the OH group and number it from the appropriate end to give the OH group the lowest possible number. And then identify the nature of the substituents and indicate by numbers where they are. So that's one example. Let me give you another example, also from the book. Now, we got a problem. And the problem is, we can see that this is an alcohol. We can see it's a benzene derivative. What do we do? Well, there is a list published by the International Union of Pure and Applied Chemistry that ranks functional groups, in other words, bits and pieces stuck onto a carbon unit, in order of, in a hierarchy. And OH is higher than a benzene ring. And so the principal group here is an OH group. Therefore, the stuff is named as an alcohol. And then the next rule kicks in, that is to say, you identify the longest chain containing the OH group, and you number it in such a way so as to give the OH group the smallest possible number. So if you number it this way, you can see that that thing is a hexanol. It is in fact a 2-hexanol. And at position 4, 4-phenyl, 2-hexanol. It's very interesting, in the textbook it calls that molecule 4-phenyl 2-pentanol, but I guess the author can't count. Now what happens if you have a double bond in the chain, or a triple bond in the chain? Well, you use exactly the same procedure. You identify the longest chain carrying the OH group, you check that the OH group is the highest ranking group in the molecule. If it is, then you know you've got to name it as an alcohol. Now, how do you check that? Well, you look at this list. How do you look at this list? Because I haven't given it to you. Well, I'm not going to give it to you. I will always tell you which is the highest ranking group. So let's now have another example in which the chain is not a saturated hydrocarbon and in fact carries some unsaturation. And the example that I will use is this one. So you look at this molecule and you see how there's a chain, there's a double bond, and there's an OH. Now what's the principal functional group? The principal functional group is the OH. It outranks double bonds, it outranks benzene rings, and it outranks triple bonds. So this thing now has to be numbered in such a way as to give the principal functional group, the OH group, the lowest possible number. So this is a 5-carbon piece. 5 carbons, you think of pentane, but this isn't a pentane, it's a pentene. So this is a penteneol. And you can see that if I put the numbers in the positions that I have put them, there is absolutely no confusion because the thing that comes after the number, its position is easily identified. The ol is obviously at position 2, and the ene is at position 4. But you can also put the numbers earlier in the name if it causes no confusion. And if you write 4-pentene, then obviously the ene is at carbon 4. And then 2-ol. So there are these two names. One of them is favoured by the United States, one of them is favoured by England. Although you may feel I have some bias, I will attribute equal marks to both of those names. But a bonus. No, not really. Not really. Okay. I've now shown you how to name chain compounds that have an OH somewhere and chain compounds that have an OH and a double bond. For OH and triple bond, it's exactly the same. And I've also shown you for OH and a benzene ring. In all of these cases, the principal functional group, the main group is the OH. And all these names end in ol. They need a number before the ol to tell you where it is. And they need other numbers to indicate where various substituents are. Now what about ethers? Well, for ethers, on the basis of what I just tell you, you can understand the systematic name that I gave you for allyl alcohol and also for propargyl alcohol. If you look back, you'll see that the names have numbers in them and to indicate where the ol and the double or triple bond is. They also have numbers. Well, they also have a part of the name that tells you there are 3 carbons. Now, what about ethers? Well, I wrote up a few examples in which I said you use the word ether and you put in front of the word the names of the groups attached to the oxygen. So it might be ethyl, methyl ether. If there's an ethyl, well, let's just draw it up. That would be ethyl, methyl ether. So that's one of the ways of naming ethers. But If the compounds are a bit more complicated, then you name one of the ether groups as a substituent. So, for example, oops, that's 1, 2, 3, 4, 5, 2 methoxy pentane. This is 1,2-dimethoxy ethane. So what we've done is we've taken one of the carbon-oxygen units, and it's always the smallest one, and we've regarded it as a substituent on the rest of the molecule. And so here we've taken this group, which is a methoxy group, methyloxy-methoxy group, and we've put it onto a carbon chain of 5 atoms, and it's put on at position 2 of that carbon chain. And once again, we number the chain from one end to the other in such a way that we give the lowest possible number to the position of the methoxy or ethoxy or alkoxy in general. Just an alkyl group on an oxygen. We give the lowest possible number to the carbon carrying that group. And here we've got a very short carbon chain, just 2 carbons, so we think of ethane, but there are 2 methoxy groups on it, and so we call that 1,2-dimethoxyethane. Now there's one other way of naming ethers, and it's often used for cyclic compounds, and that is you pretend first of all you don't have an ether, and you name the hydrocarbon. And then you put in front of that name the symbol oxa, which means you have replaced a CH2 by an oxygen. So let me show you a few examples of that. The method is also used for complicated chain molecules, but I'll give you examples only for some cyclic compounds. Both of these compounds have more common names. We call this one tetrahydrofuran, because furan is this material, and if you add 4 hydrogens, then it becomes tetrahydrofuran, but you can call it oxocyclopentane. This you can call 1,4-dioxapentane. cyclohexane, but it's more commonly called 1,4-dioxane. So there are a number of ways of naming ethers, and that makes life a little more difficult, but not too difficult, I hope. Now I want to tell you something about the physical properties of alcohols and the physical properties of ethers. And the first, I'm not going to tell you a lot, I just want to tell you something about the boiling points. The boiling point of an ether is similar to the boiling point of a hydrocarbon with the same molecular weight. So, for example, if you have diethyl ether, its boiling point is 35 degrees centigrade. If you have pentane, its boiling point is 36 degrees centigrade. So there it's rather close. And pentane and diethyl ether, they have very similar molecular weights. Because the only difference is a CH2, which weighs 14 units, is replaced by an oxygen, which weighs 16 units. So ether is a little bit heavier, but only a little bit heavier. However, alcohols have much higher boiling points than hydrocarbons of the same molecular weight. So the boiling point of this alcohol is 118 degrees centigrade, but the boiling point of pentane, 1, 2, 3, 4, well, that's funny, what a beautiful alcohol, okay. The boiling point of pentane is 35 degrees. So the alcohol, which again is only 2 units higher in molecular weight than the hydrocarbon, has an enormously higher boiling point. And the reason for that is something called hydrogen bonding. If a compound is boiling, what happens is that the molecules are all darting around inside the liquid, and every little while, one of them leaps out of the surface of the liquid. And when that happens rapidly, the compound is boiling. Now, it turns out that for alcohols, the molecules tend to stick together by something called hydrogen bonding. In a pattern like that. And the reason is that oxygen is electronegative, so there's a slight plus charge there and a slight build-up of negative charge. So a slight plus charge, slight build-up of negative, slight plus charge, slight build-up of negative, and so on. And so these alcohol molecules tend to stick together. And they change partners, but they're always associated by hydrogen bonding with other molecules. So if they're sticking together, in order for them to leap out of the surface of the liquid, they need more energy. And that's just another way of saying you have to heat the thing to a higher temperature. So that's why alcohols, because of the presence of the OH group, it allows them to become involved in hydrogen bonding. The alcohol molecules stick together, and therefore the boiling points are higher. I also need to tell you something else about diethyl ether. Diethyl ether can be quite a dangerous substance, because if you leave it in air, it is converted into a peroxide. This peroxide is explosive. And so if you have a bottle of ether, after a while you're using it from day to day, but every day a little bit evaporates, and the peroxide that's formed, I'll show you in a moment how it's formed, is not volatile. So the peroxide gets concentrated in the bottle. And if you then, every week or so, top up the bottle with fresh ether, eventually you get quite a lot of peroxide in the bottle, and one day you'll pull off the stopper and go bang and hurt you. And so you've got to be rather careful. And I'll just show you what happens. This is oxygen that's in the air around us, and here is a part structure of an ether. There it is. And what happens is, what I'm showing on the board, and this can do various things. One of the things it can do is that. And it can do other things as well. And one of the things that it can do, I'd better write it here. That does is it gives you a peroxide, so that's dangerous, and this baby is also dangerous. And those things are not volatile. They're not nearly as volatile as ether itself, so you must be rather careful. Some years ago, one of my students was simply evaporating an ether extract. He'd done a reaction, poured the mixture into water, and he extracted the aqueous mixture with ether, and he dried the ether with sodium sulfate, filtered off the sodium sulfate, took the filtrate in a round bottom flask and put it on a rotary evaporator. And suddenly there's a big bang, and his face was peppered with little bits of glass. Fortunately, he was wearing his safety glasses, so he really wasn't hurt, but he looked kind of strange for a while. So little blobs of blood all over his face. He was a big, tall, strong fellow, so the ladies still liked him. But after about a week, it was all better and he couldn't tell, but it was a bit scary. So you've got to be very careful. Okay, so now, what is it exactly that I've told you today? I told you how to name alcohols and how to name ethers. I gave you quite a few examples of trivial names for alcohols and trivial names for ethers. And then I gave you systematic naming for alcohols and systematic naming for ethers. And then I started to tell you a little bit about the properties of alcohols and ethers, and the most conspicuous property is that alcohols boil at a much higher temperature than hydrocarbons of the same molecular weight. This is because of hydrogen bonding. And alcohols also are pretty soluble in water for that reason. Ethers can also be soluble in water by hydrogen bonding with the OH groups of water. Now what I want to do is to tell you how to make alcohols. So how do you make alcohols? Well, as for many, many compounds, perhaps most, you make them from other substances. And that leads you to a problem. If you make a certain compound from another substance, you then ask, well, how do you make that substance? Well, you make that from something else. Then you ask, well, how do you make that? And so where does it all come from? Well, it all comes from petroleum. It all comes from the oil. Or almost all comes from the oil. So the compounds that one uses in order to make alcohols, there are several of them, and one of them is the business of hydrating a double bond. So if you have a double bond compound and you add an acid to it, obviously I'm not writing the full formula of the double bond compound. That is the general process for making alcohols from alkenes. And you know from last year's course that there are two ends to a double bond, and if the compound is not symmetrical, you can predict which end will pick up the proton, and consequently, which end will pick up the hydroxyl group, the OH group. And the end that picks up the proton is the end that leads to the more stable of the two possible carbocations. So that's one way of making an alcohol. It's not the best way by a long shot. And one of the reasons why it's not the best way is that the carbocation that's in intermediate can undergo a number of other processes that you don't want. There's a much better way called oxymercuration, demercuration. If you think about the meaning of those words, clearly the oxymercuration is adding an oxygen piece of some sort and a mercury piece of some sort to something, and the demercuration means getting rid of the mercury. And if you have a double bond compound and you treat it with mercuric acetate in water, get that, and then this must be treated with a substance called sodium borohydride. And sodium borohydride replaces the mercury by an H. Now, how that happens is a little bit complicated, and I'm not going to tell you the whole story, but I'll tell you a little bit of the story. So what happens is that the sodium borohydride behaves like it is a source of hydride ions, a source of H-. And the H- replaces the acetate by H. And then you get a compound like this with a carbon-mercury-hydrogen bond. And it turns out that this bond is very, very weak. And it gives a radical on mercury. And once that happens, this bond breaks to give a radical on carbon. And that radical pulls off hydrogen from another molecule. And you don't have to know that. I just wanted you to realize that there's no magic involved in the demercuration. All that happens is that the acetate attached to the mercury is replaced by hydrogen, and the resulting species, that is to say, this species, which has hydrogen on mercury on carbon, that decomposes to put hydrogen on the carbon. Now, generally, when you do a oxymercuration, when you add an oxygen and a mercury to a double bond, it follows the standard Markovnikov pattern. So, if you have this, then you will end up with that, which of course eventually gives you that alcohol. Because the mercury will come out in this way so that you get a tertiary carbocation instead of coming out this way to give you a primary carbocation. And this mercuration, oxymercuration, demercuration is generally better than trying to do an acid-catalyzed hydration of a double bond. There's one other good way of making alcohols. I have only 1 minute, so perhaps I ought to stop now.